Welcome to the Quantanix YouTube channel. This is the Next Layer Podcast, episode 11. Today, we're diving deep into AI 101, how machines learn and think. Our mission here is, well, to give you a clear, sort of intuitive grasp of how these incredible systems actually learn and process information. Moving past all the hype to the real nuts and bolts. We'll explore how machine learning has evolved, taking inspiration from basic statistical ideas all the way to building these sophisticated neural networks that are really making waves today.
Right. It's a huge shift.
It really is. It's a story of a fundamental shift, from explicitly telling computers exactly what to do step by step.
Yeah, traditional programming.
To creating systems that kind of figure things out for themselves just by analyzing data. So hopefully get ready for some aha moments as we uncover how machines can mimic and sometimes, in specific areas, even outperform human cognitive abilities.
Absolutely. And we'll be focusing on the core learning approaches that power AI. Things like supervised, unsupervised, and reinforcement learning.
The big three.
Exactly. And also how the way we teach machines what's actually important in the data has dramatically changed over time.
How so?
Well, think of it like going from manually sorting puzzle pieces yourself, telling the machine exactly what shape to look for,
Okay.
to a system that learns to see the patterns and assemble the puzzle almost on its own. It figures out the shapes and how they fit.
Gotcha. Okay, let's unpack this then. We should probably start with the foundational ideas, right? The stuff that makes all this learning possible. You mentioned statistical learning theory.
Exactly. Statistical learning theory, it provides the underlying framework for how machines learn from data. Doesn't matter if that data has labels or not. This is kind of the bedrock.
Okay.
And what's really interesting, I think, is to see how it sort of mirrors the scientific method, but, computationally.
How do you mean? Like observe, hypothesize, test?
Pretty much. We observe data, the machine builds a model based on patterns in that data, and then it uses that model to predict what might happen next with new data. It's automated inference.
So instead of a scientist with a whiteboard, the machine's building a mathematical model from the numbers. How does it jump from just seeing data points to making predictions?
It's all rooted in the idea of probability. Statistical learning theory operates on a key assumption, that the data we feed the machine is a representative snapshot, like a random sample from some larger unseen reality.
Okay, so it assumes the data isn't biased or at least represents the world it needs to learn about.
Right. And by analyzing this sample, the machine can start to understand the underlying probabilities, how likely different things are. This probabilistic thinking is why even, relatively simpler algorithms like k-nearest neighbors get better with more data.
Because they get a clearer picture of those probabilities.
Exactly. They refine their understanding. It's not about some magical intelligence popping into existence.
Right.
It's a machine getting better at calculating likelihoods based on the patterns it's seen. And what statistical learning theory really gives us is a rigorous way to approach all this. It provides the mathematical tools to build learning algorithms we can actually rely on.
So it adds the structure and formality.
Precisely. And it gives us clear definitions for those key concepts we always hear about. Like, what does it truly mean for a machine to learn? How well will it generalize to new situations it hasn't seen before?
Right. Avoiding just memorizing.
Exactly. And what happens when it overfits memorizing the training data instead of grasping the real patterns? It even gives us ways to objectively measure performance. Think of it as the rule book for building reliable learning machines.
Okay, foundation laid. So let's get into the different ways machines actually do the learning. First up, supervised learning. What's the core idea there?
Okay, supervised learning. Imagine learning with a tutor who gives you both a problem and the correct answer.
Okay, like flashcards.
Yeah, kind of. We provide the algorithm with labeled data. So for each input, we tell it what the desired correct output should be. The machine's job is then to learn the mapping, the connection between those inputs and those desired outputs by finding patterns in that relationship.
So if we show a computer, say, thousands of images and clearly label them, this is a cat, this is a dog, it eventually learns to distinguish between cats and dogs on its own.
Exactly. It learns to predict the correct label, cat or dog, based on the visual features it detects in the image. This is the engine behind so many applications you use every day.
Like spam filters.
Yep, spam filters, classifying emails, or medical imaging systems helping doctors spot potential issues. The fundamental goal is always prediction, making accurate predictions on new, unseen data based on the patterns learned from those labeled examples.
And the key is having good labels, good examples.
Absolutely crucial. The quality and representativeness of those labels, the teacher, so to speak, needs to be reliable. Garbage in, garbage out still applies.
Makes sense. Okay, what about unsupervised learning then? No teacher this time, right?
That's right. Unsupervised learning is more like an explorer heading into unknown territory without a map.
Intriguing.
The algorithm gets a data set, but with no labels, no specific target outcome. Its mission is just to discover hidden structures, patterns, relationships within that raw, unlabeled data.
So instead of predicting something specific like cat or spam, it's more about the machine trying to make sense of the data on its own, like organizing it.
Precisely. It's incredibly useful for that initial understanding of a data set. What are the natural groupings in here? Are there any weird outliers?
Exploratory analysis.
Exactly. It's also used for something called dimensionality reduction.
Which is like simplifying things.
Yeah. Think of it like summarizing complex data while trying to keep the most important underlying information. And clustering algorithms are a big part of unsupervised learning. They group similar data points together based just on their inherent characteristics.
Finding natural categories.
Yep. The goal isn't specific prediction, but really uncovering the inherent organization, the structure within the data itself. The machine finds its own categories, so to speak.
Okay, so supervised is learning with a guide. Unsupervised is exploring structure alone. Now, the third one, reinforcement learning. This one always sounds, I don't know, the most active, maybe?
It definitely involves active learning. Reinforcement learning is heavily inspired by how we, and animals, learn through trial and error.
Right, like touching a hot stove, you learn quickly not to do that again.
Exactly. Or maybe learning to ride a bike. You try things, sometimes you succeed and feel good, that's a reward, and sometimes you fall a penalty. In reinforcement learning, we have an agent.
The learner.
The learner, yes. It interacts with an environment, takes actions, and receives rewards or penalties based on those actions. Over time, the agent learns to adopt a strategy, a policy basically, a set of behaviors that maximizes its total cumulative reward.
Like a computer learning to play, say, a video game by trying out different moves and getting points for doing well, negative points for dying.
That's a perfect analogy. It really shines in tasks that involve making a sequence of decisions over time. Game playing, definitely. Also controlling robots, managing autonomous systems, even things like optimizing traffic flow.
So it's learning by doing and getting feedback?
Precisely. The agent isn't explicitly told the single right answer for each step. It'd have to learn by experimenting, exploring, and seeing the consequences of its actions within that environment. It's all about learning optimal behavior through interaction.
Okay, so those are the three main paradigms. Now, you mentioned earlier a significant evolution, this move towards feature learning. What exactly does that mean? What came before it?
Right. So for a long time, in what we now often call traditional machine learning, we relied heavily on something called manual feature engineering.
Manual engineering? Sounds like work.
It was. It meant that human experts, people with deep knowledge of the specific problem domain, had to carefully examine the raw data and decide which aspects, which features, were the most relevant and informative for the task at hand.
Give me an example.
Okay, imagine trying to predict house prices. The expert might decide that square footage, number of bedrooms, age of the house, and maybe distance to the nearest school are the crucial features. They would manually extract these specific pieces of information from the raw data about each house.
Like a detective picking out the most important clues before trying to solve the case.
That's a good way to put it. But you can see the downsides, right?
Yeah, it sounds incredibly time-consuming. And what if the expert misses something? Or focuses on the wrong thing, prone to human bias?
Exactly. It required a lot of domain-specific knowledge, and it often struggled with really complex, high-dimensional data. Think about images or audio signals.
Right. What is the key feature in a million pixels?
It's hard for a human to even know, let alone define explicitly. This manual step became a major bottleneck as datasets just got bigger and much more intricate.
So feature learning is about automating that detective work, getting the machine to find the clues itself.
Precisely. Feature learning is the big paradigm shift. It's where the model itself learns to automatically discover the representations, the features it needs directly from the raw data during the training process.
Wow, okay.
Instead of us telling it exactly what measurements to look for, it figures out the useful patterns and combinations on its own. This has been a major driver behind the incredible advancements we've seen with deep learning.
It's like the machine is developing its own senses, tailored to the data it's seeing.
That's a nice analogy. It
Right.
learns what matters.
And this connects to the idea of hierarchical representation learning, right? It sounds like the machine builds its understanding step by step in layers.
That's a great way to visualize it. Modern feature learning, especially in deep learning, often creates these hierarchical structures. Imagine processing an image.
Okay.
The first few layers of the model might learn to detect very basic patterns in the raw pixels, things like edges, corners, simple textures, patches of color.
The building blocks.
Exactly. Then, as you go deeper into the network, the subsequent layers combine the outputs from the previous layers. So, combinations of edges might form simple shapes, like circles or squares. Combinations of shapes and textures might form parts of objects, like an eye or a wheel or patch of fur.
And then deeper still?
And at the very top, the highest layers combine these complex features to understand the overall content, recognizing the entire object, like cat or car, or even understanding the scene itself.
The sources mention convolutional neural networks, CNNs, as a prime example for images. How do they specifically use this hierarchical approach?
CNNs are designed perfectly for this. Their initial layers use small filters that slide across the image, specifically looking for those simple features, edges, gradients, textures everywhere in the image.
So they find edges regardless of where they are.
Right, that's called translation invariance, and it's crucial. Then the next layers take the maps of where these simple features were found and combine them to detect slightly more complex patterns, combinations of edges forming corners or curves.
Building up.
Building up, exactly. Deeper layers combine those patterns to recognize parts of objects, and the final layers integrate all that information to make the final classification: cat, dog, car, whatever the task is.
So by automatically learning these features in this layered step-by-step way, the machine develops a much richer, more robust understanding of the visual world than if we just tried to hand engineer features.
Absolutely. It can disentangle the underlying factors that actually explain the image. Instead of just seeing a grid of pixels, it starts to perceive the meaningful components, the objects, their parts, and how they relate. This leads to much, much better performance in tasks like image recognition, object detection, and so on. It's learning to see the world in a more abstract, semantically meaningful way.
And this whole process, this automatic feature discovery on a grand scale, is really powered by deep learning and those multi-layered neural networks we keep hearing about.
Yes, fundamentally. Deep learning is, well, currently the dominant approach in machine learning, precisely because it uses these neural networks with many layers. That's the deep part. These deep networks excel at learning those intricate, complex, often non-linear relationships in data that we've been discussing. They make this automatic hierarchical feature discovery a reality, even for incredibly complex data. This is the engine behind the recent leaps we've seen in computer vision, natural language processing.
Like understanding text and speech.
Exactly. Understanding spoken commands, translating languages, analyzing sentiment and text, even analyzing complex scientific data like genomic sequences or protein structures.
So it's the depth, the number of layers that allows them to build up these increasingly complex and abstract features from the raw input.
Precisely. Each layer learns a slightly more abstract, slightly more refined representation of the data, building upon what the previous layers have learned. It's like that journey from pixels to edges to shapes to objects we talked about.
Or maybe from sounds to phonemes to words to sentences and language.
That's another great example. Deep learning architectures provide the blueprint, the structure for this automatic and sophisticated feature learning to happen.
Okay. And we got a glimpse of specific architectures, too. You mentioned CNNs for images. What about RNNs and transformers? Can you just briefly highlight what makes them good for their specific jobs?
Sure. So CNNs, as we said, are built for spatial data like images, using those local connections and shared weights to find patterns efficiently wherever they appear.
Right.
RNNs, or recurrent neural networks, are designed for sequential data. Think text, speech, audio, time series data like stock prices.
Things that happen in order.
Exactly. They have a sort of feedback loop, which allows them to maintain an internal memory or state. This lets them process sequences of variable length and, crucially, remember information from earlier parts of the sequence when processing later parts.
So they have context.
They can learn context over time, yes, although traditional RNNs had some limitations with very long sequences.
Okay. And transformers. They seem to be everywhere now.
They really are. Transformers, a more recent innovation, have proven incredibly powerful, especially for language, but also increasingly for vision and other areas. They excel at capturing long-range dependencies in data.
Meaning connections between things that are far apart in the sequence?
Precisely. Their key innovation is the attention mechanism. This allows the model to dynamically weigh the importance of different parts of the input when processing any given part. For instance, when processing a word in a sentence, it can pay attention to other relevant words, even if they are far away, to better understand the context and meaning.
So it learns what parts of the input are most relevant to understand other parts.
Exactly. That makes them incredibly powerful for tasks requiring deep contextual understanding.
Okay, that gives us a much clearer picture. Different architectures really are specialized tools for different kinds of data problems.
That's a good way to think about it. A toolbox. And, building on these foundations, we're seeing even more advanced techniques for learning representations emerge. Things like autoencoders and contrastive learning.
Autoencoders, the name kind of suggests they're learning to encode something about themselves.
In a way, yes. They learn to encode the input data into a usually much more compressed, efficient representation, the encoding. Think of it like creating a really effective summary or a shorthand version.
Okay.
The autoencoder then tries to reconstruct the original input just from that compressed version. If it can do a good job reconstructing, it means the compressed version, the encoding, must have captured the important information.
So it learns useful features by trying to summarize and then unsummarize.
Pretty much. And there are interesting variations. Denoising autoencoders, for example, are trained to reconstruct the original clean input, even if they are given a noisy or corrupted version. This forces them to learn more robust features that aren't thrown off by noise.
Clever.
And variational autoencoders, or VAEs, go a step further. They learn the underlying probability distribution of those compressed representations, which allows them to actually generate new data samples that look similar to the training data.
So they can create new images or sounds.
Potentially, yes, by sampling from that learned distribution.
Fascinating. And the other one you mentioned, contrastive learning. That sounds like it learns by comparing things.
That's the core idea. Contrastive learning learns representations by comparing examples. Specifically, it tries to figure out which examples are similar to each other and which are different.
How does that work?
Well, a popular technique called SimCLR, for instance, takes an image, creates two different augmented versions of it. Maybe one is cropped differently, one has its colors slightly changed.
Okay, variations of the same thing.
Right. And the goal is to make the internal representations the model learns for these two augmented versions as similar as possible. At the same time, it tries to make the representations of these versions very dissimilar from the representations of completely different images.
So pull similar things together in the representation space and push dissimilar things apart.
You got it. This turns out to be a very effective approach for self-supervised learning.
Meaning learning without explicit labels.
Exactly. The learning signal comes directly from the data itself, the inherent similarity or difference between augmented views of the data. Momentum contrast, or MUCO, is another related technique that uses a clever way to manage a large set of negative examples, the similar things, to make the learning more efficient.
It's really amazing how these systems are finding ways to learn meaningful things about the world, often with very little direct human guidance, just by looking at the data structure itself.
It truly is. And when we look at how these different learning mechanisms are actually put into practice, especially back in supervised learning, it often involves that process of feeding the system vast amounts of labeled data.
Right, the teacher providing examples.
And the algorithm then iteratively adjusts its internal parameters, the connections in the neural network, for instance, to minimize the errors between its predictions and the true labels it was given.
So it keeps tweaking itself to get closer to the right answers.
Exactly. Optimization algorithms, like gradient descent and its many variants, are crucial here. They guide those parameter updates in the right direction to find the best possible model configuration based on the training data.
It's a continuous process of refinement based on feedback.
Precisely. And the success, as we said, really hinges on the quality and diversity of that training data. The model needs to see a broad range of examples to learn patterns that actually generalize well to new unseen data.
And avoid just memorizing the training set the overfitting problem.
Right. The power of deep learning here is its ability to learn those incredibly complex mappings between inputs and outputs, which has led to its stunning success in areas where traditional methods really struggled, like nuanced image recognition or mastering the complex strategies of games like Go or chess.
And shifting back to unsupervised learning, where there are no labels to guide it, how does the machine actually discover those meaningful patterns or structures you mentioned?
Yeah, without labels, the machine has to find the inherent structure within the data itself. So clustering algorithms, for example, will group data points that are mathematically similar to each other based on certain distance metrics. This effectively discovers natural categories or segments within the data without being told what those categories are beforehand.
It finds the clumps.
It finds the clumps, exactly. Dimensionality reduction techniques like principal component analysis, PCA, work differently. They try to identify the underlying axes or directions of greatest variation in the data. This allows us to visualize complex high-dimensional data in a more manageable lower-dimensional space like 2D or 3D, or to compress the data while retaining most of the important information.
Finding the most important underlying factors.
Yes. And as we discussed with feature learning, techniques like autoencoders or matrix factorization, when used in an unsupervised setting, help find compact, meaningful representations of the data. These representations can often reveal hidden or latent factors and relationships that we might not have been aware of just by looking at the raw data.
So it's incredibly valuable for just exploring new domains or making sense of massive amounts of unlabeled information we're generating.
Absolutely. It's like the machine is acting as its own data scientist, exploring and uncovering insights from raw information without any preconceived notions given by labels.
That's a great analogy. And, as these AI systems get more sophisticated, we're starting to see the emergence of mechanisms that sound, well, almost cognitive, things like attention and memory systems.
Yeah, that's a fascinating area. Attention mechanisms, which we touched on with transformers, really do allow the AI to focus its processing power, so to speak.
Like how we focus our attention on one conversation in a noisy room.
Exactly that kind of idea. Attention mechanisms allow AI models, particularly when dealing with sequential or complex inputs, to selectively weigh the importance of different parts of the input data when making a decision or prediction. Self-attention in transformers is a prime example. The model learns which other words in the sentence are most relevant for understanding the current word's meaning and role.
So it's not just processing everything equally, it learns what's important contextually.
Right. And memory systems also play a crucial role, especially for tasks that unfold over time.
That makes intuitive sense. You need memory to understand a story or a conversation.
Definitely. In RNNs, as we mentioned, those internal hidden states act as a form of working memory, allowing the network to retain information from earlier steps in a sequence to inform processing of later steps.
Like remembering the beginning of a sentence to understand the end.
Exactly. And some more advanced architectures are even experimenting with external memory modules, separate memory banks that the network can learn to read from and write to. This offers a more flexible and potentially much larger capacity for storing and retrieving information over longer durations.
Almost like having a notepad the AI can use.
Kind of. It's moving towards more flexible information management.
So these systems aren't just passive processors. They can focus, they can remember. That seems essential for moving towards more complex tasks that require reasoning and decision-making.
Absolutely. And we do see forms of reasoning and decision-making in AI, though it's important to be precise about what we mean. AI reasoning can range from relatively simple pattern matching, if I see this pattern, then that usually follows, to more complex logical inferences, though the latter is often still an area of active research, especially combining it seamlessly with deep learning.
So it often emerges from the interactions of all these learned components.
Often, yes. Neural networks can learn to manipulate abstract representations derived from data and apply learned rules or transformations to new situations, which looks like a form of reasoning. And when it comes to decision-making, particularly in reinforcement learning, the system learns to evaluate different potential actions based on the future rewards or penalties it expects to receive.
Predicting the consequences.
Yes, predicting consequences and choosing actions to optimize some long-term goal. This often involves that tricky balance between exploration, trying out new things to see if they're better, and exploitation, sticking with what it already knows works well. Some systems even incorporate notions of uncertainty and risk assessment into their decision-making.
It's really incredible how these relatively simple underlying mechanisms, learning from data, adjusting parameters, can lead to such complex and sometimes seemingly intelligent behavior. But it's not all smooth sailing, right? The sources also mention challenges and limitations.
Oh, absolutely. Big challenges remain. One major one is generalization and robustness.
Meaning how well the AI performs on situations it wasn't explicitly trained on.
Exactly. While models can perform brilliantly on data similar to their training set, they can sometimes struggle significantly when faced with slightly different situations, edge cases, or inputs that are designed to fool them, so-called adversarial examples.
Right, like changing a few pixels in an image makes the AI suddenly misclassify it completely.
Precisely. This highlights the difference between sophisticated pattern matching, which these systems excel at, and genuine human-like understanding of the world. Robustness is also a concern. How well does the system perform if the input data is noisy, or if the environment changes slightly? Adversarial attacks are a specific worry, where malicious actors intentionally craft inputs to cause failures.
And there's active research on making models more robust.
Huge amounts of research, yes. Developing more inherently robust algorithms, methods for detecting adversarial examples, training models on more diverse and challenging data, it's a major focus.
Another big one mentioned is interpretability or explainability, the black box problem.
Yes, that's a huge one, especially for complex models like deep neural networks. They can have millions or even billions of parameters, and understanding why such a model made a specific decision, how it went from input to output, can be incredibly difficult.
It just gives you the answer, but not the reasoning.
Often, yes. And this lack of transparency poses significant challenges, especially in high-stakes applications like medicine, finance, or justice, where we really need to understand and trust the decision-making process.
So if a loan application is denied by an AI, we need to know why.
Exactly. There are efforts to improve interpretability techniques for visualizing what parts of an input the model focus on. Methods for approximating complex models with simpler, more understandable ones, building inherently more interpretable architectures, but there's often a trade-off. Sometimes the most highly performing models are also the least transparent.
A difficult balance to strike. Okay, looking ahead then. What are some of the future directions and implications mentioned in the sources?
Well, there are several exciting emerging paradigms. We touched on self-supervised learning, which holds immense promise for reducing the dependence on massive amounts of expensive labeled data by learning directly from unlabeled data.
Learning more like humans do, perhaps.
Perhaps closer, yes. Then there's meta-learning, often described as learning to learn. The idea is to train models that can adapt very quickly to new tasks or environments with only a few examples, rather than needing extensive retraining.
Faster adaptation.
Right. We're also seeing interest in neuromorphic computing building hardware inspired directly by the structure and efficiency of the human brain, potentially leading to more energy-efficient and robust AI. And there's ongoing work trying to better integrate symbolic reasoning, the kind of logical, rule-based reasoning humans are good at, with the pattern recognition strengths of neural networks, bridging that gap.
And beyond the technical, the societal impacts are huge.
Immense. AI is already having and will continue to have profound implications across society, employment, privacy, how decisions are made, even social interactions.
And ethical considerations loom large.
Absolutely. Issues around fairness, algorithmic bias, accountability when AI systems make mistakes, transparency. These are critical ethical challenges that need careful consideration and proactive solutions. AI has incredible potential to help address global challenges in areas like health, climate change, and scientific discovery, but its development and deployment need to be guided by careful thought, ethical principles, and appropriate regulation.
Well, this has been a truly illuminating deep dive into the core of how machines learn and think. It's complex, but breaking it down really helps.
Indeed. We've journeyed from those foundational principles of statistical learning through the main paradigms up to the cutting edge of deep learning, and even touched on cognitive mechanisms and the big challenges. That shift towards automatic feature learning really is a key takeaway.
Absolutely. And while the field is moving incredibly fast, understanding these core concepts, supervised, unsupervised, reinforcement learning, feature learning gives us a solid foundation for making sense of it all.
Precisely. And that understanding is just becoming more and more important as AI gets woven deeper into the fabric of our lives.
Thank you so much for walking us through this fascinating landscape. Really appreciate the insights.
My pleasure. Always fun to talk about this stuff.
Thank you for joining us on this deep dive into how machines learn and think. We've explored the diverse algorithms and paradigms that empower AI, from statistical foundations to deep learning intricacies and cognitive inspired mechanisms. We've highlighted that transformative impact of automatic representation learning and touched on the significant challenges like robustness and interpretability, as well as the exciting future directions. We hope this has underscored why grasping these concepts matters in our increasingly AI driven world. Thank you for tuning into the Next Layer podcast on the Quantanix YouTube channel. Please like, subscribe, and stay tuned for more in depth explorations. And maybe a final thought to leave you with. As AI continues its rapid advancement, what unforeseen capabilities, perhaps even new forms of intelligence, might emerge? And how will our very understanding of understanding itself be challenged and redefined by these learning machines?